Okay, so the problem we're going to work on is an optimization problem. And the problem states a gardener wants to make a rectangular enclosure using a wall as one side and 120 meters of fencing for the other three sides. Express the area in terms of x and find the value of x that gives the greatest area. So we're trying to optimize the area of this rectangular enclosure. And what we're trying to do is we're trying to find a dimension x that maximizes it. And we're also trying to find the corresponding dimension y that goes with that. So let's start by first drawing the rectangular enclosure. And what we're going to do is we're going to account for the fact that one side of it is going to be a wall. Right, so we'll draw the wall in black. And then the other three sides in red is going to be the fencing. So our model for this equation is going to be the area for the rectangle, right? So we're going to call the top portion x. The bottom portion also has a width of x. And then the length for the right-hand side is going to be y. So we're going to say A is equal to x times y. Okay, so this is our model. Now our constraint is going to be the fact that the perimeter of fencing that we're limited to is 120 meters, right? So we're going to say our 2x plus y must be 120. So this is our constraint. So the first thing we want to do, it says express the area in terms of x, right? So to do that, we're going to use the constraint and we're going to write y as a function of x. So we're going to write y is equal to 120 minus 2x. Now we can plug in this y function into our area function, right? So we have a of x is equal to x times 120 minus 2x. And we can write this as 120x minus 2x squared. So this is our area function as a function of x, right? So now what we want to do is we want to differentiate this function with respect to x. That way we can see if we can find any critical points that correspond to the maximum area. So what we're going to do is we're going to write a prime of x is 120 minus 4x. And we're going to set this to be equal to 0 in order to solve for our critical points. So the first thing we want to notice is that our domain for this derivative has to be 0 or greater. The reason is because we can't have negative dimensions, right? So we're going to say our domain here is 0 included to positive infinity. Okay, so let's go ahead and solve for x. So we're going to write 120 minus 4x is equal to 0. So this means 4x equals 120. And this gives us x is equal to 30 for our critical point. So this x equals 30 represents the value that maximizes the area. What we can now do is find the corresponding y value by using the function for y we derived before. So we can write y is equal to 120 minus 2 times 30. All right, so this is 120 minus 60. So that tells us that y must be equal to 60. So the corresponding y value that goes with this maximizing x value is going to be 60 meters. Okay, so there we go. So we found the area function expressed as a function of x, and we found the x and y values that maximizes the area of this rectangle.